So this definition of alpha 0, of course, let me write it down here. Alpha 0 mu was okay, and similarly I would have E R. So I would have these two terms. Now my aim is to deal with the Virasoro constraint. So what is my Virasoro constraint? My Virasoro constraint is 0 equal to del plus x mu whole square. Okay. So, and I know its value here. This is without square, so I have to take a product of these two. Okay. So this is then equal to, this is then equal to ls by square root of 2 whole square, and this is summation over, could I use this result and go one step further and absorb this into this, because this term does not involve n equal to 0, so I could absorb this term also here, and then at that point of time I would not say that n is not equal to 0. Then n is 0 also, and minus 1 to minus infinity also, and plus 1 plus 2 to up to plus infinity also. Okay, all possible integers. So I could absorb this, and this would give me ls by square root of 2 times summation of n from minus infinity to plus infinity, including also n equal to 0. Then this is alpha mu n e to the power minus I n plus. Okay. And this is what I would like to make use of. So this is my del plus x mu. Okay. And now I want to take a product of these two. So this is square, and I have double summation. Let us say instead of n, I say over n and m, and they are from the real numbers from minus infinity to plus infinity, including 0. So sum over L, sum over M, and alpha mu L, alpha M, and this is, so 1 mu comes here, e to the power minus iota. If I, so this would be L plus M sigma plus. Is this okay? What I am doing is, this is just del plus of x mu, time derivative of x mu, time derivative with respect to light front of this, and the product of these, okay, square of this. So I write summation of, instead of n, I have written L and M. Okay. Okay. So there is this term which consists of these two and a scalar product of these two, alpha mu L, alpha mu N. Alright. Now I can remove this, and here the 0 modes have been alpha 0 is included here. Okay. Now so this, now let me put L plus M equal to some n. This is not the earlier n, but this some number n. Okay. Then this would give me n equal to n minus m. I can put this here. Times. Now I would need to sum on. I'm going to remove L from there. So, did I have a factor of 1/2 somehow? Okay, now it seems my notes tell me that I should have a factor of 1/2. Did I leave it somewhere? Perhaps you could track it out. Okay, let me keep this factor of 1/2 somehow. Is it because of this? It is possible, but it should be correct. Okay, the overall multiplication factor. Okay. Then my notes are telling me correct, but I am reading it incorrectly. If this is ls divided by square root of 2 and whole square, this is 2 here, that this 1/2 is written here. Is this okay? Is this okay? So, keeping track of your lost things is good. So, this is now 1/2 alpha, L is n minus m, and of course mu, and alpha m, let me put mu here. Okay, it's a scalar product of two mu vectors. Okay, that's also, if you like, you can put it like this. Okay, it is the same thing. Okay, or you could even drop this. If you like, you can even drop this, where it is understood that this is now m is repeated, so it's a sum over m, and of course minus infinity to plus infinity, also including 0. Okay, also including 0. And so this, you write it as this or as this, 1/2 alpha n minus m alpha n. But whenever you come across such expressions, it is understood that there is a mu here, there is a mu here. Okay, just like x square is x mu, x mu. Okay, so if you like, you can drop this, but assuming that this is a scalar product of two mu vectors. Okay, because it's a mu vector, it's mu.
You must either like define n as a fixed thing or sum over n, right? You only have a sum over m.
Because m is getting repeated. So, wait. It looks all right. So,
but if you write like this is for a specific n. If you're not summing over n is it's a fixed number.
N is you are right. What actually should happen? You are very, very correct. Thank you so much. It's a serious mistake. What should happen? L plus m equal to n. I have put, and what I did with this term, I have eaten it away. I'm sorry. I should not. I'm not allowed. So here there is a product of e to the power minus I n sigma plus. So here this is e to the power minus I n Is that okay now? So, no? Now it's okay. Now it's okay. Okay, it's no longer a free index. It's no longer a free index. Okay, n is there, n is there. Okay.
So you're summing over n.
But I'm summing over n.
N.
And also.
You're
n.
only summing over m, or summing because if you say that everything that is up there is equal to what's down there, up there you have no free indices at all. You're summing over m and l. So that cannot be equal to something that has one free index, which would be n. You're summing over m and n.
And n.
Okay, now.
Okay. Thank you. Yes. Okay. And now with this, I would like to define a new object. This into this, I would like to call it, let me define it all over new here. Would I define it here? Ln is defined as summation over m 1/2 L mu n minus m alpha m and mu. Okay, and in that case I want to remove only the first step from here, and I can write it which is also is equal to this ls square, and yes, Tobias, you are absolutely correct. In Ln, you are absolutely correct. What is happening is my mind did not read. You see, now I am defining it in two steps. I am defining this and putting a summation over n here, but this definition of Ln already is having summation over n. So you are absolutely correct, and I am sorry. Yes, but we stand corrected. Okay, now we stand corrected. Very good. So, and then I would like to skip. So this is what we have done with t plus plus. Okay, so t plus plus is del plus x mu whole square, and that gives us this. And one more thing we need to notice here. You see this? It is 1 minus iota n sigma plus, and ln sitting there. What does it indicate physically to us is that ln, which we are going to call as the Virasoro operator, is nothing but the Fourier mode of t plus plus. Is that fine? That's the physical meaning, that I can expand my t plus plus into some Fourier modes, and these ln kind of objects are now going to the Fourier modes of t plus plus. Similarly, when I write 0 equal to t minus minus equal to that thing there, del minus x mu whole square, then this is going to give me ls square summation over n equal to minus infinity to plus infinity ln. Now I call it ln var e to the power minus iota n, but this should, I think this should be sigma minus, but let me still verify it. Okay, my guess is that this should be t plus plus. Yes, that is correct. So this gives me this. Let me. Is this fine? Let me write it again here. So my t minus minus as given there is expressed and 0. This is del minus x mu r whole square. This is del x mu r, but this is a function of sigma r. And this whole square, and this could then be summed up as equal to ls square n from real number equal to minus infinity to plus infinity ln bar. I don't have too many variables. Initially, instead of bar, I wanted to call it m of n, capital M or something. But then I decided, okay, let me retain L bar. But L bar has nothing to do with that L actually. It's not some complex conjugate of L. Okay, Ln bar is a separate symbol. So Ln bar and e to the power minus n and sigma minus. Okay, where now this I think we are understood, sum over all of them, sum over n here. So my Ln I can recap here. This was Ln. So let me write Ln as summation over 1/2 n minus m and alpha m and bar is 1/2 beta and minus m. This is mu, this is mu, this is mu, and beta m and mu. Okay, and this so here you write summation over m, and here you write summation over m. So both of them are being summed up, and therefore now what we had, this is one thing here, and in the other one 0 equal to t plus plus equal to ls square this ln e to the power minus in sigma plus. So this I only wanted to emphasize here, that this ln and ln bar are going to be our Virasoro operators at the quantum level. They are expressed in terms of the annihilation and creation operators or the Fourier mode. These are. Now we derive some more conditions on these Fourier modes and alphas and betas. But we remember in our mind that my ln is the Fourier mode of t plus plus, and my ln bar is the Fourier mode of t minus minus. Okay, and also because separately we have proved that alpha t alpha beta is 0, so t plus plus is 0, t minus minus is 0. Therefore, if the left hand side is 0, right hand side also has to be 0. This is non-zero, and therefore this is going to be 0. This is non-zero, and therefore this is going to be 0. So ln is going to be 0, ln bar is going to be 0, and n goes all values, including L0, minus 1, minus 2, minus 3, minus infinity, plus 1, plus 2, plus 3, plus. So they give us an infinite number of constraints on the theory, these Virasoro operators. and they obey a certain algebra which is called Virasoro algebra. Now I think I can remove all of this. All right. This I might still leave in there. One more thing, that while reading some literature, you might as well play n with m, like if you make m minus n here, then this should be n and summation should be over n. But then in that e to the power, that should be n. Okay. So different books, different literature, different articles, they use it that way, but we understand what it is. Okay. All right. All right. So now these Ln and Lm, they obey a certain algebra, and what is this? Lm Ln is equal to m minus n L m plus n plus d by 12 nq minus m nq minus m delta n plus n0, and similarly you would have would also be so you see this term, if n is equal to 0, m equal to 1, plus minus 1. So for all these three values, for m equal to 0, m equal to plus minus 1, this term would so 0 plus n 0. So this would, what happens is this term vanishes for this term vanishes for second term. Okay. This second term has a special name. It's called as this whole thing is called Virasoro algebra, and if this term is present, is called Virasoro algebra with central extension. And this D actually, which is called as the central charge, is actually identically equal to the number of dimensions of our theory. So for bosonic theory, it would be 26. Okay? And it is denoted by different symbols, sometimes C or sometimes capital D, just to say that this is called the central charge. And this term vanishes for m equal to 0, m equal to plus minus 1, and otherwise it survives. Okay? And so, but we know that we have, for example, already considered three cases: open string with NN and open string with DD, boundary conditions where alphas and betas were related, either they were identically the same, and in the closed string case. In the closed string case, alpha and beta both are different. Okay? So we know that, and for closed string we would have both of them actually, LM as well as LM bar. So we would have this algebra as well as this algebra, but for open strings we would have only this, because alphas and betas, they are related, either identically the same or alpha is equal to minus beta. Okay? But if you happen to go to more involved things like n, d and d, and then you have to again work out whether k is an integer or not. Okay? And what are the conditions on them. But these are good enough for demonstration purposes, that we consider n and d. Okay? All right. So now let us have a look little bit further. These are two things. One is in the first place, you see x mu is x mu or x mu dagger is x mu. So reality condition. Reality condition for the field. This would tell you that alpha mu n star or dagger, this would be alpha mu minus n on the one hand, and these alphas and betas would be real. Alphas and betas are real, and alpha mu dagger is alpha mu minus n, and beta mu dagger is beta mu minus n. So actually this would play an important role, and of course the number operator would be is your alpha dagger times alpha mu n, and beta mu dagger beta mu n. But you see, what would this be? This would be beta mu minus n and beta mu plus n. Okay, and similarly this would then be because alpha mu dagger, alpha n dagger is alpha minus n, beta mu n dagger is beta mu minus n. Okay, so this would have implications when you write down, when you construct the higher energy states. So what will happen is, let me better take explicit example. Alpha mu plus 1 dagger plus 1, it is enough to write 1. This would be alpha mu minus 1, and beta mu 1 dagger is beta mu minus 1. So if I have alpha mu 1 dagger alpha mu 1, this would be my alpha minus 1 alpha plus 1, and beta mu 1 dagger is beta mu 1 would be beta minus 1 beta plus 1. Is this okay? I mean, this is nothing but the creation operator, this is the annihilation operator, but this is the creation operator. So, but this is equal to alpha mu minus 1. So sometimes you rate that the negative modes correspond to the creation operators. I personally don't like this language because mathematically it's more explicit. When I have minus here, this is going to be a creation operator. When it's plus 1 here, then it's going to be an annihilation operator. Okay? Because of this condition that alpha mu dagger is alpha mu minus. Similarly, beta mu dagger is beta mu minus. Okay, beta mu n is beta mu minus n, dagger of this, Hermitian adjoint of this. Okay, so I think I could remove this. We only need to remember that this L and L bar, they are the Fourier modes of classical Virasoro constraints t++ equals to 0 and t minus minus equals to 0. Okay? When we Fourier expand t++, we arrive at these Virasoro operators. Actually, they play a very, very crucial, important role in our here, while considering bosonic theory, we have only these two kinds of Virasoro operators, Lm or Ln, whatever you call it, and L bar, L and L bar. However, when you consider superstring theory, then you would also have Virasoro operators corresponding to the Fermi part. You might denote it by any other name. Here we are denoting them by L and L bar. You might denote them by any other name. So there would be operators, and there would be mixed operators of bosonic and fermionic. This is purely bosonic. Okay, I mean the product here. Okay, the in the definition, it's Ln is sigma over okay. In particular, L0 is very interesting. This is alpha minus n, and similarly Lm bar is my 1/2 n equal to minus infinity to plus infinity beta m minus n beta n. So if you like, you will add mu here. If you like, you will add mu here, and mu, and from here L0 bar so the L0 and L0 bar, they would play a very crucial role. What happens is that when you write down, I'm not sure if I would be, how far I would be able to go today, but just to signify that you would have relations of the type and this is m eta mu delta m plus n equal to 0, and x mu p mu, this is, these are the commutation relations that would follow from the canonical quantization of the theory. They are not at the classical level. So after you achieve the canonical quantization of x mu or x mu pi mu, and then you put these modes. So, but with respect to, and similarly for the betas. So what happens is alpha 0 and alpha 0 minus m, this is equal to m eta 0 delta 0. But now you might recollect that our eta 0 is minus 1. Okay. So the point is that this would lead to the existence of states with negative norm. And negative norm states are called as the ghost states. And in your gravity theories, you consider wormholes. in some of your models where you consider some phantom fields. Phantom fields are the scalar fields with a negative energy. They are ghost fields. In Hilbert space, in quantum mechanical language, you will say that any states with non-positive definite norm or negative norm, they are the ghost states. So here you encounter that this is -1, so minus n, even if delta is 1. So this gives rise to the negative norm states. And for the elimination of these negative norm states, what you do is you demand a Gupta-Bloiler quantization kind of a condition that you have in field theory, Gupta-Bloiler quantization condition. A similar condition here you would in the first place you ask L0 to annihilate physical states. I would recap it next time, but here you ask that L0 minus A M0, this is LM, M0. So, and that means L0 minus A annihilates the physical states, and what it means, I take its permission adjoint psi and I put it between that the expectation value of this diagenesis. So this is going to help us remove these states with negative norm. We have states with negative norm, but we can rescue ourselves by the use of this kind of a condition. So with this, and this actually is needed as I had written this. So it is clear that one needs it only for L0. When M is 0, this is 1. So this is A here, but when M is not equal to 0, this term drops away. So only L0s annihilate the physical states. But then we replace, and this actually has a deep significance with the number of extra dimensions or the total number of dimensions of the string theory. Okay, which comes out to be 26 for bosonic and 10 for the Bernoulli. So this guy A is going to play a crucial role for the elimination of the negative norm states on the one hand, and for fixing up the total number of dimensions of our string theory on the other hand. And this we just do by requiring or demanding that the expectation value of L0 minus A is 0, or by just saying that L0 minus A annihilate the physical states. Okay, so L0 minus A, L0 is a constraint, Virasoro constraint. So in any case, the physical theories, the physical states are those states that are annihilated by the constraints of the theory. And here L0 minus A is the constraint of the theory. We are making a generalization, replacing L0 by L0 minus A. And this would help us remove the negative norm states on the one hand, and help us in fixing up the number of total number of dimensions of our string theory on the other hand. So with this, I think let us conclude for the day. I thank you all very, very much. Okay, thank you very much.